Hey there, my fellow intellectuals. Happy Black Hole Week to all of the space lovers out there. For those of you who may not know, this is a week designated by NASA to celebrate everything and anything related to black holes. And if you don't know me, I'm someone who is getting a PhD in the Department of Physics and Astronomy at the University of California, Irvine, specializing in supermassive black hole mass measurements. So I effectively try and weigh supermassive black holes that live at the centers of galaxies. One particular example of this is the black hole in M87, which I have shown behind me here. So these are two different images of M87. The first one is the famous Event Horizon Telescope collaboration picture taken in 2019. And on this side, you have a reconstruction of that image that was just recently generated this past month. So it is an exciting time for black hole research. And for this particular video, what I'd like to do is I'd like to show you a talk that I gave at the American Astronomical Society Meeting in January 2023 on a very preliminary black hole mass measurement that I am working on for my PhD dissertation. So it was a 5-minute talk that I gave at this conference. But unfortunately, there was some sort of a technical mishap. So the first minute or so of that presentation was lost. But what I will do instead is that I will recreate that first minute here and now, and then I will stitch in the presentation I gave at the conference at the end. So without further ado, I hope you enjoy the presentation on a preliminary black hole mass measurement I am doing in the galaxy ESO 208 G21. Hello everyone, my name is Kyle Cabasaris. I am a 6th and final year PhD candidate in the Department of Physics and Astronomy at the University of California, Irvine, and I'm here to tell you about some preliminary results of a black hole mass measurement our collaboration is conducting with ALMA and the Hubble Space Telescope in the galaxy ESO 208 G21. To start this talk, I want to give a brief introduction as to why measuring the masses of central supermassive black holes is particularly important. Over the past 2 decades, astronomers have found that the masses of central black holes correlate with large-scale properties of their host galaxies, such as bulge velocity dispersion, bulge luminosity, and bulge mass. So these relations suggest that the black holes and their host galaxies co-evolve together through cosmic time and influence each other's growth. We need a large sample of reliably measured black hole masses to fully understand these relations and figure out what they imply about the roles black holes play in galaxy formation and evolution. In the figure here, we can see the M-sigma relation being plotted with black hole mass on the y-axis and stellar velocity dispersion on the x-axis. We also hope to understand the role that supermassive black holes play in regulating different aspects of galaxy formation and evolution. So our collaboration has been obtaining ALMA data since about ALMA cycle 2, and there is a growing number of high-resolution ALMA datasets of circumnuclear disks from both our collaboration and others. So we've been doing this since about ALMA cycle 2, so I'll be showing the velocity fields here of some of these disks that our collaboration as well as others have obtained. But today I'm going to focus in particularly on this one, ESO 208 G21. Okay, so this galaxy is a lenticular galaxy about 14 megaparsecs away from us on Earth. And like I said in the previous slide, if we zoom into the very, very center of this galaxy, we see a circumnuclear disk that in the previous slide I showed the velocity field for that we can study to infer the central black hole mass. Now I will say that our collaboration has already measured a number of black hole masses using the kinematics of cold molecular gas with ALMA. And so if you're interested in learning more about what our collaboration has done over the years, these are the different galaxies we've obtained black hole masses of and references that are associated with those works. Okay, so how do we actually measure the masses of these central black holes? So we build what are known as thin disk models. They dynamically model the rotation of a thin disk that is in the gravitational potential of the supermassive black hole and an extended stellar mass distribution, or the mass of the host galaxy. The free parameters of this model include the disk position and inclination angle, the supermassive black hole mass, which we care most about, and the stellar mass to light ratio. Now, one thing that you should know is that ALMA data comes in the form of a data queue. And so what we do is that we
from these thin disk models, generate synthetic data cubes that model the observed CO data. So what you're looking here is the observed CO kinematics of the disk on the left, as well as my model on the right. And we fit our models directly to the data via chi-squared minimization. So our preliminary result for the black hole mass in the galaxy ESO 208G21 is about 210 million solar masses. So our models are able to reproduce the observed features in the ALMA data fairly well. So we have here moment maps of the surface brightness, rotational velocity, and gas velocity dispersion on the right there. And particularly if we look in the middle row, that's the velocity field, we can see that our our model fits the data fairly well with some minor discrepancies at different parts of the disk. So the next step in the work is to determine the mass measurements error budget. So what I'm going to show you here now is a m-sigma relation plot with all of our collaborations, previous measurements, as well as the ESO galaxy that I'm currently working on right now. So I'm going to be spending some time working out the error bars of this measurement. And we know from previous work in our collaboration that one of the biggest limiting factors in these black hole mass measurements is central dust extinction. So these disks are very dusty, and that affects the amount of stellar light that we actually observe, and thus has an important effect on the measured black hole mass value that we derive. And so I will be using two-band color map information from the Hubble Space Telescope to work out how much extinction is in the very center of this galaxy, or at least try and quantify it in some reasonable way, and see how that affects the resulting black hole mass. And with that, I just want to thank you for listening to my talk. I'd like to thank my collaborators for all their support. I want to apologize. There are a number of ALMA black hole related talks that our collaboration is doing, as well as posters on dust. So very briefly, I'll just mention today there is posters from 5:30 to 6:30, numbers 270.01, 270.02, and then tomorrow we have talks on ALMA related black hole stuff in room 2A in this afternoon session. And with that, I will end my talk and I'll take any questions you may have. Thank you.
Well, this is a very interesting work. Questions? I do have a few. What comes to my mind are the measurements, the direct measurements of black hole masses using IFU data. Nicholas McConnell, those papers ring the bell. How is your method using ALMA better than using IFU?
Right. So it's a really good question. The question here is essentially asking how IFU, stellar kinematic data, compares to the gas dynamical methods that I'm using here. So one of the things about stellar methods that is very powerful because every galaxy, of course, has stars that we can model. The problem is that, not the problem, but one of the difficulties is that you have to model stellar orbits that go well outside the black hole sphere of influence into the outer regions of the galaxy, whereas these disks are only a few arc seconds long at the very, very centers of these galaxies. So we're probing very, very close to the black hole sphere of influence with ALMA, and so we don't have to worry too much about what the stars are doing in the very extended farther parts of the galaxy.
Well, that's wonderful. So your error bars will be a little bit less than what they have for the IFUs, because I remember that they have big error bars.
Yeah, so that's a very interesting point. I will say that for some of the measurements, it really depends on on how well we resolve the black hole sphere of influence. So in some of these galaxies, particularly NGC 3258 and NGC 1332, we actually got re-observations of higher angular resolution observations with ALMA after the initial ones, and we were able to dramatically reduce the error bars of those measurements. And so this is sort of a first pass with ESO 2AG21, but I can imagine if we got higher angular resolution observations, we can see a decrease the error bars all derive with this case.
Yeah, that's great. Then how long does it take for you to derive the black hole mass of an elliptical galaxy?
Well, it mostly depends. I think building the initial model is not that long once we have all the data and the HSC data. The biggest time sink is definitely with the dust correction, which I really want to emphasize how important this is to account for the presence of dust in the central parts of these galaxies. We've seen in some of these measurements, like in previous work at the uncertainties can be 20, 30, 40%, if it's not properly accounted for, even larger in some cases. So
okay, that's fantastic. Yeah. Okay, let's thank our speaker again. Very much.
And with that, that is the end of the video. I hope this gave you some appreciation for black holes this Black Hole Week, and it gave you some idea as to what it's like to give a presentation at a professional conference. So with that, I hope you have a wonderful day, and I will see you in the next video.